Chemistry in the PM. I'm your host, Mr. Shindelka. Today we're looking at electrochemical cells. Right now, traffic is flowing smoothly on College Avenue. It's about 30 degrees outside, light winds, variable cloudiness. Let's return. Okay, electrochemical cells. If you're watching this on video, please pause the video, jot this down. I will talk about it in a second. Okay, I'm assuming you've paused and you've copied this out. Let's go through this diagram and we'll talk about it. Now, this is a beaker, this is a beaker, right? We've got two different chemical solutions. First of all, in this particular example, I have a zinc strip here and a copper strip on the right. A zinc and copper battery combination is like a Duracell and stuff. Say the copper top, anyways, it all says. This is a simplistic battery, it works. Obviously, a Duracell battery is a little bit different. Anyway, the negative end of a battery is called the anode. Anions are negative, anodes are negative. The positive side of a battery is called the cathode. Cations are positive ions. Cathodes are positive ends of a battery. Most people outside of chemistry only talk about anodes if you talk about batteries and stuff, attach it to the anode, and they use it interchangeably with positive. Anyway, this is the negative side of the battery. Why? Because it's giving out negative electrons that flow and are attracted to the positive cathode side. When that happens, the negative electrons build up on this copper strip. I have a solution with copper ions in it that will be attracted. They're positive. So they kind of neutralize, and you're going to get copper buildup on that strip. At the same time, you're losing positive ions here. So this salt bridge is just to complete the circuit. The positive deficit will be taken up by the salt. KNO3 is one example. And we choose that because both potassium and nitrate, they don't form solids, remember, from solutions and solubility. Potassium, group 1 elements don't form solids. You can use sodium or something else. Nitrates never form solids either with most things. From this end, let's think about this here. When it loses electrons here, it's losing the electrons from the zinc. So the zinc loses electrons and then it throws out zinc ions into solution, positive. Now, to equal things out there, you got ions from the potassium nitrate to migrate in to just complete the circuit. Okay? Now, this anode will be eaten away over time. Anybody ever pay attention to what happens to their water heater? Servicing, nobody helps out? Yeah, do you do anything every year or two called replacing the anode? Okay, you don't, nobody helps out with the parents. No. Or if you rent a water heater, you get somebody to come in every once or 2 years, depending on the company, and you replace the anode. Why? Because our water's so hard here, there's ions in it, and it eats away at an anode. They put it there on purpose so that it eats away at this anode that's then replaced every 2 years, a stick. Instead of your iron, like the actual tank, being eaten away. It has the anode that's eaten away, okay? And there's electricity flowing through this. That's why I have a voltmeter in the center. It could be a light bulb. Now, something to jot down. So, a memory aid. Red cap. Reduction happens at the cathode. If you remember that, then you know the oxidation happens at the end. And this particular one, these are the reduction and oxidation path reactions. I'm going to pause. You pause the video, jot this down. Okay, I'm assuming you mark that down or copy this down. These half reactions are referring to this side. The copper is receiving 2 electrons to make, the copper ions are receiving 2 electrons to make regular copper. That's what happens here. And the zinc is losing electrons to make the ions. The lost electrons e to the copper, right? This is all referring to. Providing electricity. Now some summary here. I'll just get you to center that. I'll pause the video. You can copy these things down too. Okay. As some of you are just finishing up writing, I'll just talk through this stuff here. I've got in blue, first of all, the anode, oxidation. Strongest reducing agent. Anyways, anode's negative. Anions are negative. Get that in your head. It produces electrons, negative charge. Cathode, red cat, reduction at the cathode. Red cat. It accepts the electron. And it's positively charged. That's the positive end of a battery. Okay. These are simplified batteries. They're easier to understand. They actually work. Of course, the Duracell batteries and lithium-ion batteries and stuff, they've kind of got a paste instead of a wet solution. But a car battery has actual lead plates in it. And then it has sulfuric acid as the solution in there with ions in it, stuff like this. That's why if you ever spill a car battery or whatever, it's got the acid all over the place. Excuse me. Okay, back to this recording. Red cat, remember this, because I'll be asking, which is the reduction, which is the cathode. The ions in that salt bridge, I'm not, just because we're abbreviating things this year a little bit, I'm not going to get you to do a heck of a lot, but if you take chemistry in university, you have a little better. The anions in the salt bridge go to the anode, the cations go to the cathode. You can always figure that out, though, because is it creating a buildup of positive or negative charge? You figure that out. And you use a salt that doesn't form a precipitate. KNO3 is the one I go to when we do actual labs and stuff like this. I use potassium. But we won't this year because of time constraints. Now, let's just see. Let's figure out the charge of that copper zinc battery, and this is the work we need. So, this is a very simple redox equation. So we use the same steps. The first thing that we do is separate it into two half reactions. And I think after doing the balancing half reactions are a lot tougher than this. This will be easy. So I've got the copper ion, one copper. I've got the zinc, one's the zinc ion. Plus. Okay. So. Well, then after that, this one's super simple as far as the electrons. As far as the electrons, because there's no oxygen and hydrogen to balance them, right? So we skip straight to the electron thing after we got this. The high side on the copper is the 2+, the 0 is the low side. So to bring 2 down to 0, we need 2 electrons on the left-hand side. Zinc, 0, is an element. The zinc 2+. The 2+ is the high side on that one. We need 2 electrons. Now, I purposefully left some space on the right-hand side because we're going to do an electrical add-on here. On your periodic table of elements handouts. In the middle, you will find a sheet that says standard electrode potentials for half reactions. Pick that up right now. I'll pause the video while you. Handout set, electrode potentials for half reaction. Okay, so you're locating on your handout set. Is this freezing on me? Okay. On your handout set, you have this sheet. What you're looking for is, you're looking for the one that involves the copper and copper 2+, but everything is written as half reactions adding electrons, reductions. They're all reduction potentials. So you're going to have to flip one. So one of them will be backwards, one will be forwards, right? You're looking for copper and copper 2+. Hey, this is it. Right here, copper 2+ plus 2 electrons, 0.34. And you're looking for the zinc one. The zinc one is zinc 2+ plus 2 electrons to regular zinc, -7.6. Okay, so you guys find that? One of them has to be flipped. I'll just go back to the sheet here. I'm going to write that down directly as it was written. You don't normally write this down. I'm only writing it down because I'm recording and someone can't see what I'm doing. Okay? So I'm going to pause the video. Okay. I just wrote down what's on the sheet at the bottom, only so that you can see. You don't have to rewrite it. Now, when you look at it, the copper is an exact match as is. It's the reduction. Everything on the chart is reduction. What I'm going to do right now is write down beside the copper reaction, E with like a degree symbol in the electricity. And we'll say that's the positive, 0.34 volts. Now when I look up the second one, you'll notice that it's written backwards. So, if it's reduction, it's -76, negative decimal points. If it's got running in reverse, it actually gives out positive voltage. So we're going to write down positive 0.76. Okay, so when you reverse a reaction, you reverse a half reaction. When you reverse a half reaction, you reverse the sign of the voltage. Okay, and now you just do the arithmetic. Happens to be 1.10. Now, those voltages listed are only for solutions of 1 volt per liter at 25 degrees Celsius. Temperature affects batteries, and you know that when it's 40 below and you're trying to turn over your car, the battery, okay. The actual concentrations do affect things too. So this is for one specific set of conditions, but it gives you an idea what are good combinations and stuff. Copper and zinc are a great combination. They're not necessarily the highest voltage possible, but copper and zinc are relatively cheap materials. So that's why you see so many copper, zinc, copper. Well, it fluctuates in price, but relative to gold or some of the other things on this list, and it's also not explosive and stuff like that too. It's relatively safe. So some of the things, like lithium batteries are great. You notice that lithium is at the bottom of your electrode list? That means when it's flipped around, it gives off a lot of positive charge, like, you know, when it's the oxidation reaction, lithium-ion batteries are great. They're more expensive, though. So you know how Duracells tend to be in your cheap toys and stuff like that when you were kids and stuff? That's why, because they're very disposable, and you don't have to worry about when you throw them away. They're not as toxic. You really shouldn't throw batteries away. You should take them back to a store where they can recycle them. Anyway, so that's the math behind this. One other thing here. This is easy, though. Add these up. If you have the electrons balancing, this is easy. It just turns into what we started, but I want you to show this. And this is easy. other thing I want you to show is red cap. Which one's reduction? Because that's the cathode reaction. Copper is being reduced. So I'm going to say red cap, just as a reminder here. And then I'm going to say cathode. I want you to write the full word, and then anode is the oxidation. Now, this is the example. Pause. This is the example from the diagram that I gave you, right? Now, on the actual assignment, don't look at it right now, but on the assignment, I'm giving you two things that are reacting. You got to come up with the reactions and then the diagram. Fill in the blank. But once you have which is the cathode and anode, just watch. And I'll redo this without looking back. Okay? And with the salt bridge, because that's going to be on your diagram. It's up to you guys. Negative or positive on the left? I think I heard negative. Okay. I don't really care. Just be prepared for the negative to be on the right. I'll give you one of the sides. Now, your whole goal is, now you have this diagram already done, but I don't really care right now. Reductions at the cathode. Anode is the zinc one, right? Okay. So from knowing which is the cathode and which is the anode, the negative side is called what? Anode or cathode? You're going to label it, right? You're going to say, okay, now I'll just do this in a different color here. Everything else is like what you need to know. If I give you this black diagram, you're going to say, well, the anode's on this side. Well, this must be the positive. This is the cathode. You're not redrawing this. You're just kind of following the logic. Right? Okay. And the cathode and the anode. Okay, we got that labeled up here. The cathode is the copper reaction. The anode is the zinc one. So the anode, I'm going to label this as zinc. This as copper. And the zinc reaction is giving off electrons, so the electrons are going from the left to the right. You'll label the electron direction, right? Now this is on your original diagram. So this is cool. Yeah. The electrons are being delivered to the copper. Copper ions, when the electrons reach there, are in solution and they're going to build up more copper on the strip. Likewise, for oppositely, I guess, at the anode, the zinc is being eaten away because it's losing electrons and they're going into solution. Because you get an extra zinc in there, that means the salt bridge will deliver the negatives to balance out the charge to the anode side. It will deliver positive ions to the cathode side because it's losing positive charge. Essentially, that's what you have to label. I forget it. But before I turn you loose to do that diagram question, I'm going to do one more example. Let's go for, this is the one we just. We'll see this. I'll see if these ones are actually on there. I might have to give this voltage line. Jot down A. Don't worry about B yet. Sometimes I make these lists with a different text, but I think I'll have to give you the cobalt one. I don't know. I don't see cobalt. Okay, doesn't matter, I have it. down. Okay. So let's figure this out in two half reactions, right? So I got the cobalt, or the cobalt 2 plus. I see that the high side, I'm going to move that over. The high side's on the right in this case. So I'm going to add 2 electrons right away. Then the iron. The high side is on the left, so I'm going to add 1 electron. Okay. Now we look these up on a chart. And when you look it up, as is, iron is on there, the cobalt is not. I'll give you the cobalt. It would be positive 0.28 volts. I'll give you ones when you have a test, ones that you have down. So don't worry. What is the iron when you look it up on the chart and make sure it's in the right direction? Actually, it is in the right direction. I'll let you catch up. Pause the video, catch up to this. What is the iron from the iron sheet? What is the iron? 3 plus to 2 plus. 77. Good. And it's positive, written the way it is. Okay. I'm not going to just blindly add this up, though. In case we have to do something. Now, I already flipped the sign on the 0.28 volts for you from a different section. Okay? But what do you notice about the electrons? Because we have to have everything balanced. You need to multiply the second equation by 2. 2 here, 2 here. That makes it easy. We do not, and it's the way, and I won't get into the physics of it, it's the way voltage is joules per coulomb, and don't worry about that. Did you guys take that in electricity in physics? It's too much to cram in. Anyways, you do not multiply. When you flip, you change the sign, but you do not multiply to 77. Okay? That makes the math easy. Doesn't matter if it was 3 or 5 or 2 or 1. But now I can add up the equations, and it's just as you suspected. Cobalt plus 2 iron, and cobalt ions plus 2 of the iron 2 ions. Maybe you just do the simple arithmetic, and you're 105. Okay. What you have, volts. What I want you to do is try 2 more problems. Sometimes you will have one of them being negative. If you ever get something that adds up totally negative, that just means it doesn't happen spontaneously or on its own. It's actually, that would be in recharging state, like where you plug in your phone, you're recharging your battery, it's working in reverse. Yeah. Okay, mathematically, it's without a sign, it's assumed positive. Is that what you mean? Yes. But if it's negative, you definitely should. I'm emphasizing that. Because before I had the color choosing, the electrons didn't match. It was 1 electron. Okay, yeah. You still have to make sure of that, but these are way simpler than the other problems. By the way, most of your things, if you're looking at your half reactions, you're getting stumped with the electrons. Look on that sheet. It has them all there too with the electrons balanced for the half reaction. Okay? You might have to multiply it by 2 or 3, but it's a good start. So for B and C, one of those does involve some electrons and so on. But for C, for example, the MnO4, Mn2 plus half reaction, just look on your ion sheet and all the hard work's done for you as far as balancing with water and stuff like that. It's already there for you. Try B and C. This is a break time right now, though. I'll give you guys a few minutes break. I'm going to just show for the people on the video the answers to B and C. So pause, try these. Here are your answers to B and C. I'll pause right now. And then once you do these, finish the redox assignment, okay? That's your instructions for those of you trying this at home.